For, I guess, my final video, I would like to do U substitutions with definite integrals. And the way I do definite integrals is slightly different than I do indefinite integrals, but not the initial steps. I'll show you what I mean. I'm going to start with my first example, an integral from 0 to pi over 4 sine of x over cosine squared of x dx. Now when you're investigating u and du possibilities, one of the things you might try is u equals sine of x, because the derivative of sine of x is so easy. It's just cosine of x dx. And so when you'll do this, then here's what you'll get for an integral. You'll get a u there, but see, the problem is down here you do not have cosine of x dx in the denominator. So, and then even if you did have a dx in the denominator, you would have something weird like this, and we do not simply have anything that deals with the du squared. And unless, I guess, we're doing something like a double integral, we're not. And having the du down here is verboten anyways. So don't do it. It's not going to work for you. Usually you're going to find what you need in the denominator, because when you let u equal something from the denominator in du, it will always make sure that the dx stays atop of any types of fractions. So what I'm going to do, this, I don't take away from your trial and error learning, but that's where you will learn the most. I'll get rid of those, and I'll show you what I would let equal to u. That would be u equals cosine of x, not cosine squared, because if I did cosine squared, I'd have to deal with that 2 coming down, cosine of x, and then take the derivative of cosine, and I would get sine x, and I don't have cosine x sine x as a product anywhere in there, so I'm not going to do it. Just cosine of x. You'll learn how much you can get away with later on. We take the derivative. Derivative of cosine of x is negative sine of x dx. And of course, I have sine of x dx all in the numerator. Not negative though, so what I'll do is I'll take the negative out of here and I will put it in front of my du. Then it's all a matter of substituting everything. So let's go ahead and put it in. Okay. Where I do things different is in the limits of integration, and we'll deal with that in a second. Right now, let me go ahead and rewrite the problem in a way that you'll understand how I'm doing the substitution. Remember, cosine squared of x is the same as cosine of x squared. So since I'm still dealing with x, I'm not going to monkey with these things just yet. So then we'll go to the next step. Is where I'm going to start putting in my u. So down here I'm going to have a u squared in the denominator. In the numerator I'm going to have negative du. This is an extremely simple integral. Now, here's where I do things a little bit differently. You can go ahead and do your integration now. But what I recommend doing right at this moment is changing the limits of integration. Because when you switch to u, while it's still integrating inside of this rectangle per se, it's a different rectangle than 0 to pi over 4 and whatever height that is. What you do is, in the land of x, x went from 0 to pi over 4. When you make a substitution like this, as x goes from 0 to pi over 4, u is going to be doing something totally different. And so how do we find out what that is? Well, let's go back to u equals cosine of x. Now what I can do is, when x equals pi over 4, I can do u of pi over 4 equals cosine of pi over 4, and everybody knows that one to be radical 2 over 2. So my upper limit, instead of pi over 4, will be radical 2 over 2. And in the denominator, in the lower limit of integration, I had a 0 there before. Well, u of 0 equals cosine of 0, which equals 1. Now, when I finish the problem, I won't have to substitute back to x because I've already made the transition to full u. So I won't have to plug in, like resubstitute sine of x or cosine of x back in for u. I can just use these numbers in my integration. Let me do another step here of the integration. I'm going to rewrite this as, I'll pull the negative out front. I have 1 to radical 2 over 2. U to the negative 2. I think it's a lot easier to integrate something when it's in power rule format than in any other format. And of course, you add 1 to the exponent and divide by the exponent. So I get negative u to the negative 1 over negative 1 from 1 to radical 2 over 2. And now I'm ready to use the fundamental theorem of calculus, where I plug this as my upper limit in, and then I plug my lower limit in. I'm going to do one last piece of simplifying before I do any of that, though. These negatives will cancel with each other, and I find thinking of a number to the negative 1 power difficult for me to compute it, more difficult than if I change this to just 1 over u. So I'm going to change that to 1 over u from 1 to radical 2 over 2. And now I'll go ahead and do my plugging in the upper limit minus plugging in the lower limit. So I get 1 over the square root of 2 over 2 minus 1 over 1. Remember, you don't have, there's no c anymore, because if you remember when we did the fundamental theorem of calculus, I had an f of b plus c minus an f of a plus c. The c's canceled each other out, so there's nothing to worry about there. So I will simply end up with 2 over radical 2 minus 1. And there is, for definite integrals, you'll always get a number. Let me scooch back to the last indefinite integral we did. And you notice the last indefinite integral we did is a function. But these definite integrals are numbers, so long as the limits of integration, of course, are numbers. Another example. Let's do the integral from 0 to 4 x over the square root of 9 plus x squared dx. And what you might want to try by pausing the video to take a stab at what you might let be equal to u and see what you can do with it. But then I'm going to, what I would use is, I say to take as much as you can. I wouldn't take just x squared for my u, because when I took du I'd get 2x, but you could just divide that 2 out, so that's working well. Why not do x squared plus 9? Because then when I do take the derivative, when I do my du, the 9 just disappears anyways, harmlessly. So that's what I mean by taking as much as you can. I don't recommend letting u be the entire square root, because then when you take its derivative, you're going to get something over a square root. It's not going to be pleasant. Actually, it might not be terrible now that I'm thinking about it, but you're not going to like it if you're new to this stuff. So I'm going to satisfy myself with doing u equals 9 plus x squared, and then du equals 2x dx. And if I scan my integral, I do not have a 2x appearing anywheres. So I think it's better to have du over 2, get rid of the 2 over on the right if I can, and then notice I have x dx, which is perfectly what this numerator is, this x dx. And so the x dx part becomes du over 2. And the 1 over square root of 9 plus x squared becomes 1 over the square root of u. Also, the limits of integration are not going to remain the same. If I put 0 in place of x, I will get 9 plus 0 squared will give you 9. Now, if I put 4 in place of x, I will get 9 plus 16, which is 25. Now what I like to do in my next step is to make this the most friendly type of an integral that I can possibly imagine. So in one step I'm going to take this 2 and pull it out front as a 1/2. I'm also going to rewrite this as a power rule problem. So I get 1/2 the integral from 9 to 25 u to the negative 1/2 du. That equals 1/2 times, now remember, add 1 to that, so you'll get u to the positive 1/2, and divide by exactly the same amount, 1/2, and you will be going from 9 to 25. The 1/2, if I flip it, it'll become a 2 in the numerator, so I can technically cancel this 1/2 with that 2. And so I just have u to the 1/2, so I get 25 to the 1/2 minus 9 to the 1/2. Well, that's just the square root of 25, which is 5 minus 3. And I thought this might be a good integral to see if I actually did it right. And there's a way of checking yourself on these with your own calculator. Go back to the original problem. What I'm going to do is take the x over the square root of 9 plus x squared and put it into y1. So I'll clear whatever was there from before, and I have then x divided by second, where's that square root again? There it is. 9 plus, and at least this version of the calculator, the vinculum atop of the square root increases as I write stuff underneath of that bar. I don't have to worry about getting out from underneath it because that's the end of what I'm going to write. And I'm going to just do zoom 6. Now what I want to do is I would like the integral from 0 to 4. So what you do is you go second, and above the trace button is calc. Do you see number 7 is a little integral symbol? Take the number 7. Now once the lower limit, so x equals 0 is our lower limit, so you hit enter. The upper limit, our upper limit is 4, so I'll put a 4 in there and hit enter. Now watch what it does. It'll actually fill in the area. It's kind of hard to see. You can see the answer is 2, which agrees with ours, but if I were to change the window a little bit, you'll be able to see it. Let me make the window, the x min will be -1. I'll go from -1 to 5, so I have a little bit of buffer. And at the y, I'll go from -1. I don't think it went very high. Let's try 1 to 1 and see what happens. Now I'll do that integral again. So I go to second, calc. I'll choose number 7. Lower limit will be 0. Enter. The upper limit will be 4. Enter. And you can see, watch, there it shades in the area so that you know that this is the area that you're getting. The answer is 2. Our answer was also 2. So you can use this to check yourself. Now, your calculator, depending on the model, may not give you an answer like this, but what I would always do with something like this, and now that I'm looking at that answer, I probably would have rewritten it as radical 2 minus 1. Same thing, I just simplified. What you could do is have your calculator run the answer, and it'll give you a decimal, and then compute this and see if the decimals match up. That's all you really got to do. Of course, your instructor, like me, will require you to show these steps, so you can't just put an answer like this and expect to get credit for it. Another example, I have the integral from 0 to the natural log of 4 e to the x all over 3 plus 2e to the x dx. So what I'm going to do is let my u be the entire denominator. You see, a du will definitely involve an e to the x. This e to the x will still be around, but e to the x is part of the derivative as well, so that's perfect. So if I let u equal 3 plus 2e to the x, du will equal to 3 will go away, and I'll get 2e to the x dx. Of course, that 2 in the front is no big deal. I can easily handle that by dividing by it. And now I see I have a perfect e to the x dx for that portion, and I have a u in the denominator. So this equals the integral. Oh boy. Put it again. The integral, now let me throw in my numbers. 0. If I throw 0 in for x, I'll get 3 plus 2e to the 0. Well, e to the 0 is 1, so that'll be 5. Then if I plug in ln 4, well, e to the ln of 4 is 4, so I'll get 2 times 4, that'll be 8, plus 3 will be 11. And then let's go ahead and replace the things I need to. I'll have 1 over u, that'll be the denominator portion, and then the ex dx, I'll have a du over 2. And x is forever to be forgotten now. I'll pull the 1/2 out. I think by now perhaps you can follow what I'm going to do. The 1/2 is no big deal. I'm really integrating 1 over u. And the integral of 1 over u is the natural log of the absolute value of u. And I'm going from 5 to 11. That equals 1/2 the natural log absolute value of 11 minus 1/2 natural log of the absolute value of 5. Now 11 and 5 are positive numbers, so I'm going to do a little simplifying. I got 1/2 the natural log of 11 minus the natural log of 5. I can combine that into one natural logarithm if I want to. Honestly, if you were to leave an answer like that, I'm fine. But I'm going to go further. It seems like I feel like I have an obligation to do so. The rule when you have a subtraction with natural log is you divide. So you do ln 11 over 5. And then if you wanted to even go further, you could. One of the things you could do is take the 1/2 and make it a power on that. So if you wanted to, you could write a very compact natural log absolute value of 11 over 5 for your final answer if you would like to. Now let me show you how you can check something like this with your calculator, even though your calculator will give you a decimal. We will put this stuff into the calculator. Now I don't know if I can do that ln 4. Let's see what is possible with our calculators. So let me turn it on again. Let me clear. And I'll go to y equals, clear that out. And where is my e to the x? E to the x is above ln. So I'll go e to the x. You've got to come down from that exponent, divided by, and put the denominator in parentheses since you have a sum in there. Even if you didn't, I still think I would do it because I get nervous, especially when my denominator gets large. So I got my e to the x. I'll come down from the exponent, finish my parenthesis. We're going from 0 to ln of 4. Well, ln of e is 1. So we're not going a large distance here. So I'll start with the zoom 6 and then see what happens. Boy, it's a tiny little thing, isn't it? All right. I don't care about it. I just right now I want to see if I can get these numbers in there. So I'm going to go second calc, and I'm going to choose number 7. Okay, my lower limit is 0, so that's good. I'll hit 0. The upper limit though is the ln of 4, and I don't know if I can plug. I don't know if it'll let me do this. Hey, look at that. I'm honestly surprised. So I don't think you have to add in the parenthesis, but let's see what we get. Now it did shade that in. I have 0.394 for my answer here. Now what I'll do on here is I'll enter this and see if I get the same number. So remember, 0.394 is the calculator version of the answer. Let me go and do second quit. That'll take me out to the main screen, and I'm going to do natural log. And we will do the square root of 11 divided by 5. And I'll come out from under the square root. This, because I have to end the parenthesis, that's a good idea to do that. Let's see what we get. See that? 0.394. I feel fully confident my answer is correct because I get the same decimal. couple of trig identities that you should probably know. Let me remind you of this one, cosine of 2x. You may remember that there was a formula for a sum of two angles with cosine. And the way it worked was you did cosine of x times cosine of x. Now, with cosine, you didn't get a plus next, but you had a minus. And then you did sine of x times sine of x. I'll tell you where it comes from. Usually I see an A here and then a B here. So you'd see an A here and then a B here and then an A here and a B here. So you get the idea. Well, it ends up being cosine squared of x minus sine squared of x. A couple ways you can redo this. If I go through and try to make all cosines here, here's what happens. I'll get cosine squared of x minus, remember sine squared equals 1 minus cosine squared. Alright, and then I'll do a little simplifying. Notice that I'll get 2 cosine squared of x minus 1. Now let me go back up here where it says it equals cosine of 2x. I'm going to solve for cosine squared, not cosine of x, just cosine squared. So I'm going to add 1 and divide by 2. So I will get cosine squared of x equals 1 plus cosine 2x over 2. We're introducing this now because practically from the first day of Calculus 2, you'll be expected to have this memorized. So there's one trig identity for cosine squared of x. I can convert it. Why is this such a big deal? Because I can integrate the right side. The left side on its own is very tricky. Now, let me come back to this cosine of 2x business, at least back to where it was cosine squared minus sine squared. So I have cosine of 2x was equal to cosine squared of x minus sine squared of x. This time I'm going to solve for sine, so I'm going to replace cosine squared with 1 minus sine squared of x. And I end up with 1 minus 2 sine squared of x. What I want to do then is solve for sine squared, so I'm going to subtract 1 and then divide by negative 2. So I'll get cosine of 2x minus 1, and then I'll divide by negative 2. A little simplifying gives me the following identity. Multiply through by the negative in the denominator, and I'll get 1 minus cosine of 2x over 2. So there's the one where you can take sine squared and use this identity, and then you've got one for cosine squared. Notice, the way I kind of memorize it, it's the same kind of structure for each one of them, except I just remember that this one seems like it's favorable to cosine squared, and this seems like it's not favorable to sine squared because of the plus or minus. That's how my brain remembers it. So whatever you got to do, go ahead. You'll be expected to have this memorized and add it to your arsenal of trig identities practically immediately. All right. So here's how we work these things. If you are given the integral cosine square root of x dx, if you try to go right off to a u and try to do something like u equals cosine of x du will equal negative sine of x dx. Well, the problem with this is there's no negative sine of x. There's no sine of x anywhere to be found in this thing. So this will not do anything for you. So get rid of it. Do you no good. Instead, you need to use the identity I just showed you. So you get 1 plus cosine of 2x over 2 dx. And then to work a thing like this, I would go one step further. I would take the 2 out front and put it in and make it a 1/2. The integral 1 plus cosine of 2x. Now I'll put parentheses around it because it's not attached to that fraction. Now I can almost do it, except I can't really do this straightforward unless I do something like this. U equals 2x du equals 2 dx. And what you see here is I don't need a 2 dx, I just need a dx. So I'll divide by 2 and take it out of there. Here's what I have. 1/2 the integral 1 plus cosine of u times du over 2. That equals 1/4 integral of 1 plus cosine of u du. And now you just go ahead and work it like you would any other problem. 1/4 u plus sine of u. Since this is a definite integral, I'll add the c in here. And then when dealing with a definite integral, you'd simply plug in your numbers at this point. So that's how you got to work with these things. All right, let's do an example to illustrate how we would work this with a definite integral. This time I'll go 0 to pi over 4. I'll do cosine squared 8 theta d theta. So of course I just went through all the trouble telling you to get this out of the square format, and I can do this now. I can go from 0 to pi over 4. One plus cosine. Now remember, you did whatever x was, you had 2x. So your x here is 8 theta. So 2 times that is 16 theta divided by 2 d theta. I'll bring the 1/2 in front. And I'm left inside with 1 plus cosine 16 theta d theta. Now, if it was just cosine of theta, I would know what to do. The integral of cosine of theta is sine of theta, so it wouldn't be that big of a deal at all. However, I don't have anything like that, so the natural thing to do would be to let u equal 16 theta du over 16 equals d theta. Let's see if you can deal with what I just did there. 2 steps in one. So I'll get 1/2. Now let's throw our numbers in. If I have 0 for theta, well, 16 times 0 is still 0. Pi over 4, if I replace theta with pi over 4, 16 times pi over 4 is 4 pi. And then I'll have 1 plus cosine of u times du over 16. Let me take that 16 out front. I have 1 over 32, 0 to pi over 4, 1 plus cosine of u du equals 1 over 32 u plus sine of u from 0. I can't believe I put that a pi over 4 over there. 0 to 4 pi. Well, this is really interesting, because at this stage, watch what happens to the signs. I'm going to have 4 pi, replace u with 4 pi, plus sine of 4 pi minus 1 over 32 of 0 plus sine of 0. Well, what I end up with here is sine of 4 pi is 0. I'm going to write all the details down, so if you just happen to come back and look without actually listening to me, you'll see exactly what all these numbers were. Sine of 0, of course, is 0 also. All I've got left is 4 pi over 32, so I end up with pi over 8. My next example involves sine. I'll go the integral from 0 to pi over 2 of sine to the 4th theta d theta. Of course, there's no rule that says that you're going to make this 1 minus cosine of 4 theta. There is no 4 theta rule like that. Instead, what you got to do is you're going to have to go from 0 to pi over 2 and change this to sine squared theta times sine squared theta d theta. If I were you, I would not change something to cosine. It's going to introduce a bag of worms you don't want to deal with. It'll just complicate. It's going to be bad enough as it is. So I'm going to use the rule for the trig identity that I just told you about. But for the sine version of it is 1 minus cosine 2 theta over 2 times 1 minus cosine 2 theta divided by 2 d theta. Next thing I'm going to do, I'm going to factor out, or take the 2 and the 2 to the front of this thing, and I'll get 1/4 the integral from 0 to pi over 2. I have 1 minus cosine of 2 theta times 1 minus cosine of 2 theta. Now, for a lot of people right now might be looking at me, or not me, they're looking at their screen right now, and they're probably at this point looking at it in horror that I might actually multiply this thing out. Yes, I am going to multiply it out. As horrible as that sounds, it's just a FOIL method. Let's see what happens. I will end up with 1. When I do the 1 times 1, was it first? And then you've got the outer one, so I'll have negative cosine of 2 theta, and then I'll have another negative, so minus 2 cosine of 2 theta. But then I will have plus cosine squared of 2 theta. I'll put the 2 theta in parentheses just for that one because of the squared that's involved. D theta. Now, if that wasn't enough to terrify you, I'm going to use the trig identity on this cosine squared of 2 theta. So 1/4 the integral from 0 to pi over 2. 1 minus 2 cosine of 2 theta plus 1 plus cosine, remember this is now 4 theta, divided by 2, just this quantity is divided by 2, d theta. Now, I don't know how much you want to do right now of the integral, but what I'm going to do is rewrite this piece here. This is what I usually do. Whatever you want to do, you'll develop a style, all your own, hopefully. I'll have 1 minus 2 cosine of 2 theta. Now what I'll do with this is I'll break this up into fractions. I'll get plus 1/2 plus cosine of 4 theta d theta. Notice I have a 1/2 and I have a 1. I'll combine that. Of 1/4 the integral from 0 to pi over 2 3/2 minus 2 cosine of 2 theta plus cosine of 4 theta d theta. At this stage in my life, I've mastered what the antiderivative of these things is going to be. I'll tell you what they are, and you can do what you want. The antiderivative of cosine of 2 theta, by this time in my life, I know is going to be sine of 2 theta divided by 2. Cosine of 4 theta will be sine of 4 theta divided by 4. I'm not going to do that here. I'm going to actually do these. But see, the thing is, the problem with this integral now is that if I let, what am I going to let u equal? Am I going to let it equal 2 theta or 4 theta? You've got to pick something. Only one thing will do. Unless I do something like this. 1/4 the integral from 0 to pi over 2 3/2 minus 2 cosine of 2 theta d theta plus 1/4 the integral from 0 to pi over 2 cosine of 4 theta d theta. Now, I'm not really sure what you want to do here. If you want to use different if I picked a u to be 2 theta, du over 2 equals d theta. But that would only be for this integral. So I would do something like this. But for this integral, I would let u equal 4 theta. Now, I don't know if it's a good idea to allow u to use the same letter for twice, two different things. I don't think it's such a good idea. I don't want to say it's not good form, but it's something that could probably really wreck your answer, especially if it's a complicated problem. I would not in any way, shape, or form recommend that you now use u to equal 4 theta. Instead, I would pick something like w. In fact, it's irrelevant what letter you pick. You can pick x if you wanted to. So anyways, dw over 4 equals d theta. So for this piece, I will do that kind of a substitution. So I think this is the safest thing to do. Alright, on this one, I think I have made a mistake. Let me go back up to what happened. And I see where the mistake is. Right here, you'll notice when I broke this up into a sum of fractions, I had the 1/2 here, but I did not carry the 1/2 to the cosine of 4 theta. So let me get it attached to that. And then I got to keep adding it. 1/2. What happens then is you've got this 1/4. 1/4 times 1/2. This piece will be a 1/8. Alright, now let's see what the new integrals look like with their substitutions. I'll have 1/4. The integral, when theta is equal to 0, u will equal 0. When theta equals pi over 2, 2 times pi over 2 is pi. And then I'll have 3/2 minus 2 cosine of u. D theta was du over 2, which of course I'll put that 2 out front, but let me go and work the second integral now. We have, when theta equals 0, w will equal 0. And then when theta equals pi over 2, w will equal 4 times pi over, that's be 2 pi. And we're dealing with cosine of u. Not u, I did get caught with that. Cosine of w, but then I'll have dw over 4. So I'll take this 1/2 and bring it out front. I'll get 1/8, the integral from 0 to pi, 3/2 minus 2 cosine of u du, plus, and over here I'll do the same thing. I'll take the 4 and bring it out there. 1 over 32, the integral from 0 to 2 pi, cosine of w dw. This equals 1/8. I'll have times 3/2 u minus 2 sine of u, and that will go from 0 to pi, plus 1 over 32. This is just straight up sine of w, and I will go from 0 to 2 pi. I love these pieces because this thing's just 0. Let's go ahead and get what we have. I have 1/8 times 3/2 pi minus 2 sine of pi minus 1/8 3/2 times 0 minus 2 sine of 0. That's this portion. And then I'll have plus 1 over 32 sine of 2 pi minus 1 over 32 sine of 0. Practically everything's 0 in this problem. Sine of pi is 0. This whole thing is 0. All of this is 0. All I'm really left with is this 3/2 pi, and there's 1/8 in front of it. So we have 3 pi over 16, and that is the end.